Throughout this course, we are continuously throwing out terms and not always explaining them. We assume that a normal English speaker will be understand enough to grasp what we're talking about, but in some cases that might be a little dangerous.
One term we continually use is calling things models. Now there's a massive rabbit hole behind this word which is worth exploring. So in this video we're going to look at models.
Oh, not that sort of model.
Well, maybe not, but it highlights the word model has a lot of subtly different meanings. In fact, it takes the Oxford English Dictionary over a page to cover all 34 meanings. What we need is the definition that we've been using in these videos. We consider a model to be anything that is used as a representation of some aspect of the real world.
If we go back to the start of this course, we introduced the idea of a system model, which is a model we take to represent the thing we're looking at. But having all these different sorts of models that are mentioned, often referring to things that seem very different, they all represent some aspect of the system which we're used to improve our understanding of the end product.
In our videos we found one exception to this definition. We talked about flight models, which is the term used in the space industry to designate spacecraft that are actually going to fly. It is an extension of the terms test model, prototype model, structure model, which these are proper models in that they represent the flight hardware for the purposes of the test. The flight model does not represent the flight hardware, it is the flight hardware. But you can see how when looking at a production run with all those models, the term flight model just seemed to fit. And lo, we have yet another meaning of the word model enter the language.
But in all the other cases that we're looking at, it is something that we use to represent something else. Now, if something is going to represent something else, there will be a relationship between them. And so we need to look at those relationships. Models are about relationships. Relationships in two senses. There are the relationships that connect one part of a system to another, and the relationships between the model and the real world. There is a tendency for engineers to think in terms of numbers. How big is it? Or how much power will it require? But in fact, we should be asking a different question. What makes it that big? Or what controls the power demand? That's a relationship. There may be a numerical answer to how big, but it depends on something else, some other input. So the critical thing in the relationship is between the input and the output. We could even draw a simple block diagram that might look like this. That's a model. Similarly, we need to know what the relationship is between what the model does and what happens in the real world. If the model says it should be this big, we need to ask things like, if I build it this big, will it fall down? We might even ask a rather deeper question, which is, what are the limits of the model to predict the answer to that question? Because a model is a representation of something we believe tells us about some aspect of what's happening in the real world, or what we expect to happen, in terms of the relationship between the input or inputs and the consequences. You will see that we have constructed a little block diagram here. We do this sort of thing all the time. It provides an indication of how things are connected, what the relationships are, a simplification of a situation that our minds can grasp. We're looking at something we're using to represent something else, a process we call abstraction. We build a model to simplify the problem, maintaining the characteristics of the real system in all the aspects we're interested to us, but ignoring everything else. That relationship connecting inputs and consequences tells us about the limitations of the model. In this simple example, it can tell us about how big you should build something, but it won't tell you whether you should paint it blue, for instance. It will also not give you a good prediction about what will happen in the real world if you get the inputs wrong. Or even worse, that bit in the middle, the relationship is wrong. And that last concern is with very detailed models, particularly computer models, that we've become accustomed to use, because the computer says that it is so doesn't make it so.
It is important to realise that all models are simplifications, that is, they are abstractions, and the only thing they need to possess is a representation of some aspect of the system that is accurate enough to serve its purpose. So here we have a model of a Tyrannosaurus rex. Clearly it is something we would call a model. Indeed, physical models like this are probably what you first think about when hearing the word model. But it is highly abstracted. It is only the 3D morphology that is shared with the real-world Tyrannosaurus rex. The same can be said for this model of an aircraft. It cannot fly or do anything that a real aircraft can do. It just shows you what an ME-262 looks like. And here is an artist's mannequin. And as a representation of a human form, it's not as convincing as the designer saw or the aircraft model. But what it shares with human beings is the articulation. So it can be moved into positions that a human can to help the artist compose a picture without using a real person as an artist model to pose, which will be expensive and probably will not stay as still. Again, we can see the model is abstracted so that it only keeps the important features that it is modelling. Now, the same principle applies to those models that are not physical. For example, any diagrams or picture can be seen as a model. Another class of models are analogues. These are models that are not geometric equivalents but have some similar relationships. So here we're using one thing whose behaviour we understand to compare with something quite different, but we think might behave in the same way. For example, we could use rivers and streams as an analogue for traffic on a road. Some of the behaviour of flowing water, for which we have a good understanding, could then be applied to our understanding of traffic management. At one time, it was common practice to model system behaviour with electrical, as opposed to electronic, circuits on devices called analog computers. These predate digital computers, as we can see here, with one installed on a World War II battleship. Also from World War II, in the first video we mentioned that the B-29 Superfortress bomber had gun control computers. Again, these would have been analog computers. These computers were not only used to provide predictive gun control of guns, but they were also able to model performance and stability of control systems and also things like river and traffic flow. However, these days, digital computing manages such simulations with greater ease, much more precision, by using mathematical models. Which brings us to another type of model, mathematical models. Whenever we apply maths to analyse a problem, we're using a mathematical function as a model.
All these sorts of models are used in engineering generally, and in systems engineering specifically. So what roles do they play? From an engineering perspective, models are used for the analysis of the design before we've built the system. That is, to produce data to guide the design process, to find optimum design solutions, and to understand the impact of design decisions. We also use models for qualification, to verify that the design will meet the requirements, or perhaps to extend physical test data to cases we cannot test. We also use them to sell the system, that is, to show potential customers and other stakeholders what the system will do. This is having an increasing impact as computer graphics improve. And we use them as training tools. Mathematical simulations of the system can enable training of operating personnel either before the actual product is available or where the operation is dangerous. Physical models have always been used for this purpose, but now there is an increasing use of software models. Understanding the function that a model is to perform enables the right level of abstraction to be determined. Oversimplification can give misleading results, but undersimplification means that too much work and a danger of missing the big picture in the detail.
In this video, we want to mainly concentrate on mathematical models, but before we look at them, we should say a few things about diagrams. Now, you might not think a diagram is a model because we do not generally refer to them as such. But if this three-dimensional scale representation of an aircraft is an almost archetypal model, then why not a two-dimensional scaled representation of an aircraft? After all, the original 16th century meaning of the word model in English was an architectural drawing or scale model. Drawings can often convey a lot of information very concisely, as summed up by the old adage, a picture is worth 1,000 words. Before computer-aided design, all manufacturing instructions in every industry were based on drawings. The move to computer files from drawings is only a couple of decades old and is still not complete. Until the 1970s, drawings were copied from the originals, which were on transparent paper, by putting them in contact with light-sensitive paper that produced a negative copy of the original with a blue-black background. A process that was invented in 1842 by the astronomer and all-round clever clogs John Herschel. These copies were called blueprints for very obvious reasons, and we still use that term to mean any engineering drawing. The other form of drawing that we frequently use to convey information is the block diagram. Basically, these are used for illustrating clearly how the system is being divided into elements and what the main interconnects between those elements are. They're a lot easier and more digestible than a written description or an illustration of the elements in their actual physical relationship. In this sort of diagram, blocks represent elements and lines show interconnections, the very essence of a system. Indeed, we used a block diagram to get across the concept of the system model, a model of a model, if that's not too weird. Block diagrams are one class of diagram that we generically call networks. A network is just a topography of nodes and interconnecting paths, and one of its advantages is generally they are readily understandable without explanation. Indeed, we have been using them throughout this course already. One piece of terminology to note is that if the position on the network matters, it's called hierarchical. Otherwise, it's called non-hierarchical, and only the interconnections matter. An example of a non-hierarchical diagram is a flow diagram, and we have already used this to show the flow of activity in the concept design phase of a development program. Functional flow diagrams are familiar to most people. They are networks where the elements are functions that are logically dependent on each other in a serial manner, that is, one follows after another. They flow through the path. The functions and processes are shown in rectangles and they're placed in sequence, and the decision points, which are shown in diamonds, lead to branching. When used in computing, the decisions are normally limited to two options because computers work in binary, but for more general use, more than two splits from a decision point is possible. Now, when I was taught flow diagrams, I was only shown the rectangles and diamonds, but if you pull down the PowerPoint menu, it offers you a plethora of flowchart symbols. Now, there is an ISO standard which defines the many other box types, such as those shown here. Now, the main use in systems is where functions are located in serial, and it enables exploration of the logic of the system as the various functions take place. This is why they work so well on computer programs which can only do one process at a time, and indeed they are much admired by the computer software industry and often taught as part of programming design, but in the real world of software production they are in fact rarely used. Probably the bigger users of flow diagrams is operations planning. It enables tasks to be placed in the sequence they need to be done, with branching depending on the circumstances, essentially designing an operation so that it can then be easily encapsulated into a procedure. Now let us look at an example of a hierarchical network known as a family tree. These are of little analytical value, but they are useful for illustrative purposes. They are purely hierarchical in that connections only go up and down between levels, not across to other nodes on the same level. Hardly a surprise, as their main role is to illustrate where elements fit relative to each other in a hierarchy. A classic family tree is a management organisation chart with the boss at the top all the way down to the workers at the bottom. Every organisation has one of these. But they can be valuable in other situations, for example breaking down a system into its subsystems and elements. Another example, which is shown here, is the management structure of work activities described in something called work packages, and not surprisingly these are called work package breakdowns. And we've seen another example of hierarchical networks when we looked at function analysis. Here we have both hierarchical links as the analysis progresses and cross links at each level representing the interfaces. As we explained in the function analysis video, these sorts of analysis are more often conducted within a computer program than they are on sheets of paper, which highlights a key point about networks. They can be represented by matrices and hence can be mathematically analysed. Indeed, one of the most used modelling programs, MATLAB, is at its core a matrix mathematical tool. That's how it's got its name. It's short for Matrix Laboratory.
So now we turn to mathematical models. These are of particular interest because of their apparent potential for precision and their ability to capture complexity in a way that enables us to explore the underlying workings and get a greater understanding of what we're modelling. There are several characteristics of any mathematical model that we should consider. The first is the nature of the model. This can be either static or dynamic. Static models model a single point in time, whereas a dynamic model tracks the behaviour of the object as time progresses. To be more specific, dynamic models use a particular technique to model time. At the core is a static model which is given an initial input, but which returns an altered state as an output. That altered state is then fed back as a new input, which creates a new output which is again fed back, and this is repeated, and thus the behaviour over time is created step by step. Another factor that characterises mathematical models is whether they're deterministic or stochastic. Deterministic is where the output of the model is solely dependent on the input. That means every time it is run it will produce the same result. In the functional analysis video, we even defined a function as a process that creates a determinable output state from a given input state. But I'm afraid we're going to have to muddy the water a little here with the idea of stochastic models, which produce an unpredictable output for a given input state. In short, it will not produce the same result every time that it is run with the same input. The reason is a stochastic model does not produce the same output is because it contains a probability function or even functions. So although the output is not a fixed value, it will follow a defined probability curve. And when using these models, the goal is to find that probability curve.
A classic form of stochastic model is known as a Monte Carlo analysis. This is based on something called the ergodic theorem, which says that the probability distribution over many runs will equal the probability distribution of a single run over time. In complex models, thanks to computers, this is by far the easiest approach to getting an answer to how a system with uncertain processes will behave. The way it works is to repeatedly run the model and record all the results, and then, after doing enough runs, plotting all these results will produce the probability curve we are looking for. The theory was developed by early computer pioneers von Neumann, Ulam and Metropolis after the Second World War. It was part of the work on atomic bombs as a means to model fission and fusion processes. The first computer-based Monte Carlo programs were run at Los Alamos in 1953 on very early computers. Here is an example of a Monte Carlo model that I used in a paper where I was trying to find the optimum size for an upper stage for Skylon, given that there are uncertainties in the mass of upper stages and the support equipment that is required to be launched with them, which is called Airborne Support Equipment or ASE. Now, the model generated values for the actual low Earth orbit where the upper stage is deployed, and the mass of the ASE and the upper stage. All three of these functions had random variations to model mass uncertainties in the early stage of design. Then the performance to the target geostationary transfer orbit was calculated. The model revealed a very skewed distribution, showing that designing the upper stage larger than nominal is the optimum strategy. The logic here is that if you cannot use the extra capability of the stage, the performance penalty is rather small. But if you can use it, the payoff is large. Looking at this as a lesson for using Monte Carlo models, note that despite using 20,000 trials, the resulting plot still has a lot of random noise on it. So although the trend is clear, it is a very ragged curve. Now here is another Monte Carlo from past research of mine, and this model produces a distribution with very sharp edges. The point to be made is that the curves are very smooth, and that is because it used 500,000 trials. So the lesson here is that to do Monte Carlo models, you need to run the models hundreds of thousands of times, even millions, if the curve is complex and you want fine detail. And that can cause a problem. This model needed 1.5 million random numbers, but computers do not produce real random numbers. What computers actually produce are called pseudo-random numbers, which are generated by a series like the one shown here. It works by entering an initial integer value for I, and then because the result is always an integer value, it can then be used as the next input, thus creating the series. Now the series of integers that this creates all lie in the range from a to a times m, and all of them will be divisible by a. So if we now divide each of the integers by m times a, we get a range of numbers between 0 and 1, which is what the computer outputs if we ask it to provide a random number. To give an example, here a equals 13, m equals 89, and the seed equals 5, and then we get the sequence shown here. Actually, this sequence repeats after m, that is 89 numbers, which is the best that such series can provide. They cannot go further than the value for m. But beware, it's very easy to get the sequence to repeat in less than m, so care needs to be taken. Also, if we want millions of numbers, we need to ensure that m is at least in the millions. Now in practice, m is normally pretty much the largest number that the computer can hold, and a is also very large. As a result, and with careful selection of the seed, a very good pseudo-random number series can be generated. But if you're doing serious Monte Carlo modelling, you do need to check that the program you are using is producing a good pseudo-random series for the number of trials that you are doing. What this Monte Carlo model was exploring was the question that if you have three numbers, is there a relationship between the average and the product? I was actually dealing with probabilities, so I was really only interested in the cases of numbers below 1, but here I'd widened the scope of the model to try and understand the maths that was going on. And that's the problem. The model was giving the right answers, and I could determine the boundaries through algebraic mathematics, but when I looked at the distribution of the results between the two boundaries, I found a strange discontinuity. And when there were more than three numbers, more of these discontinuities appeared. Now I could not work out why they were being generated, and ended up consulting the University of Bristol's mathematics department for help. They replied that this sort of thing was actually a well-known problem, which was found when looking at the relationship between arithmetic and geometric means, and the solutions could be found by considering the problem in logarithmic space. But as the head of department reckoned it would take him a couple of weeks to solve, I decided that I did not really need to know why the discontinuities occurred after all, and just tiptoed away from the problem. Now my point here is that Monte Carlo models will give you an answer, but they might not give you any insight as to why that is the answer.
And that brings us to the third aspect of mathematical models that we need to consider, which is, what is the underlying basis for the maths? In Mark's examples, he knew the basis for the maths, even if he did not bother with some of the details that he did not need for the analysis he was doing. When we generate mathematical models, we normally understand the physics and other principles on which they're based. But what if things are so complicated and messy that it's not practical to build up our model from their first principles? In these cases, we can build up mathematical relationships based on empirical data. That is, looking at past experience and plotting relationships between a parameter that can be established and a parameter that is of interest. So it's known as empirical modelling or parametric modelling. And this is the opposite of analytical models, where the mathematical relationships are defined from the logical consideration of the system. In complex situations, empirical modelling can provide surprisingly accurate results if there is enough background data. The trick here is to make sure that the data the model is based on is applicable to the situation you're using it for. So here we have three distinguishing features that we can use to categorise mathematical models.
So having established these three categories, let's look at a few examples. A finite element model of a structure to establish stress within it is a static model. There's no time element. It is deterministic as it gives a single answer, and analytic as it uses our understanding of material behaviour. However, when these models are used to explore the structure's resonant frequency, then they become dynamic models. Another widely used finite element model is computational fluid dynamics to establish the flow of a fluid around a shape. The name gives the game away here. Of course, it is a dynamic model. It tracks the flow step by step as it passes over the shape. It's deterministic in that it gives a single answer, and it's analytic as it's based on our scientific understanding of fluid behaviour. Another example is passenger traffic models, which both airlines and airline manufacturers are interested in. Now, there's many approaches to doing this, but they're normally static and they are deterministic, but they will be based on measurements of current traffic without really having an underlying analytical base as to why that's the case. So this model is empirical. To take another example, models of control systems on aircraft or spacecraft to ensure stability and adequate control authority, well, they're dynamic as we are looking for behaviour over time. They are analytic and they are normally deterministic. But if there is a human response to be added into the chain and into the analysis, then the uncertainty could be incorporated in using stochastic functions. Dynamic modelling was only really possible with digital computers, and this technique was born in the 1960s as these sort of machines became more widely available. Forrester of MIT was one of the early pioneers of computer-based dynamic modelling of control systems. But then he caught megalomania and started modelling things like factory industrial relations, and then cities, and finally the whole Earth. These studies came to generally very negative results about the potential of human industrial civilization. This work was then extended by an MIT team fronted by husband and wife Donella and Dennis Meadows in a large study that was funded by an organisation called the Club of Rome and was published in popular form in 1971 in this seminal book called The Limits to Growth. They used an upgraded version of Forrester's model and reached the same conclusions that industrial civilization could not be indefinitely sustained in the 21st century. It caused a big sensation when published and is still very influential in the environmental movement, especially among neo-Malthusians who believe that industrial civilization must eventually give way to a post-industrial society. Because these global dynamic models are well publicised and every little problem with them has been well chewed over, they make a good case study for mathematical modelling techniques and some of the issues with them. Forrester's model, which was called World 2, uses 115 equations to define the relationship between the various parameters of interest in the world economy. The Club of Rome modelers used a larger model called World 3, which used even more relationships. Now, the data and mathematical relationships in both the models are obtained from a combination of empirical and analytical methods. It is establishing these relationships that makes global system modelling such an expensive exercise, needing large grants to do it well. In the 1970s, these models could only be run on large mainframes. This gave them even more credence to the results. It comes from a computer, so it must be right. And only people with access to large mainframe computers and the budgets to buy the time to run them could check the results from the MIT team. These days, the models can be run on any old desktop and anybody can play the game. The world state is defined by 6 parameters, as shown by this typical output. The strange form of it is because the computer output was to a teleprinter, so the curves are produced by printing letters. The lines are drawn on afterwards by hand. Now this brings us to the first concern. Despite their complexity, it is clear the global dynamic models are a gross simplification of the real world. Now, this would be okay if the behaviour the model exhibits corresponds to the behaviour of the real world, that is, the results are valid for the use they are intended. Now, the first abstraction problem is that of those 6 parameters, only population is directly measurable. The others are vague generalizations which are composed of many related factors, which means it's difficult to actually track how accurately the model is modelling the real world. The one thing we can track, which is population, is in fact being slightly underpredicted. The main criticism of the model's abstraction that caused even some in the MIT team to rethink was that the original model did not include any effect for technology advancing as time progresses. In other words, it was made too simple. Subsequent researchers found if factors were introduced that assumed materials technology could find substitute for resources and that pollution could be more controllable with new technology, many of the pessimistic predictions of the model could be reversed. However, the actual mathematical relationship between technology advance with time and the impact it has on resources and pollution has not been possible to definitively nail down, either empirically or analytically. So in the end, whether you believe this will change the pessimistic conclusions or not depends upon personal judgment. So the model results cannot be treated as irrefutable, but then again, neither can they be dismissed. This diagram is taken from the Limits to Growth book. Indeed, it is the first figure in the book, and it tries to show how open-minded and far-seeing the authors are. In fact, what it shows is that they treat human activity as being confined to the Earth, so they model the global system as having no external interfaces. This was the main problem identified by several in the space community. If space industrialization is added into the model, such that energy can be cleanly generated by space-based systems, and resources can be increased by extraterrestrial mining, then the impact on the models is to show continued indefinite growth. These particular results were produced by an old colleague of mine, Tony Martin, but other researchers got very similar results. Martin introduces space-based industry from 2040, and you can see that it allows the continued growth of mankind's economies. The issue now centres on whether space industrialisation can be achieved in sufficient quantity and in time. As you might expect, these results were presented to the MIT team. Specifically, when the space industrialisation lobby presented Dennis Meadows with the idea of large space colonies to resolve growth issues, his response was, well, maybe, But surely that's not the future we want. In other words, he does not see the demise of an industrial materialistic civilization as a bad thing. He believes that the limits to growth will force mankind into what he considers to be a better way of life. Now, of course, the space enthusiast who use the models to show how they lead to a continued economic growth are also biased in favour of that solution. They're arguing that the models show you must go into space to maintain growth, but they also see a future of a materially rich people with access to the entire solar system as a desirable future for mankind. So even if there is agreement that the models are producing realistic results that should be taken seriously, there's still a strong element of personal judgment about what a good outcome is. Now, fortunately, in systems engineering, these sort of problems are normally resolved by reference to the needs and purpose. Global dynamic models are deterministic. That is, they always give the same answer for the same input. The implication is that for a given state of the global economy, it will always move broadly in the same direction. Now, the modelers do explore options in policy, but the underlying assumption remains that a given policy will inevitably lead to a given set of results. In real life, the global economy and human affairs is influenced by random, that is, completely unpredictable events. If you consider the human response to global warming or the COVID pandemic, it highlights how unpredictable it can be. And there is no way of capturing it in a deterministic model. Indeed, I'm not sure if there is even a stochastic way to capture it. So the question that hangs over the modelling is, do these random elements affect the broad conclusions of the modelling or not? This is a very debatable point. Things like the population growth curve do seem deterministic. The Second World War is the only event detectable in the historical population growth curve, and one has to look really hard for that. The effect of climate change, technology impacts and such factors are completely random and may change the model's behaviour, they may not. So we've used this rather unusual model to highlight 4 concerns that you should consider on every mathematical model whose results you are going to use. Any and all of these could prove an issue affecting the validity of the model for its stated objectives. Well, Bob, I know there's something that we both feel very strongly about, which is using models that are appropriate to what you're trying to do, rather than just grab the first model that you can, like, for example, finite element models, where people do a drawing, they immediately find that element model.
I think that's important. This is a class of things you're going to come across almost inevitably in your engineering career. They'll come in the form of finite element modules for stressing, for computer fluid dynamics, for flows. There are thermal analysis programs. They all work in a similar way. You have an underlying model, which you probably don't even see, which is supposed to represent the basic physics that is dealing with the phenomena, and you provide a net that provides you with the volume that you're going to do this in, and it then works out and integrates by finite element methods. They can be static simulations. Finite element model of stress is static. It can be dynamic. After all, computer fluid dynamics is basically dynamic, and you can do transients in it. They provide pretty coloured pictures, which are very attractive and give you an insight into things. And they represent a major advance in engineering design, let's face it, that came out of the latter part of the 20th century. But one of the problem there are a number of issues with these things. First of all, they're finite element models, and the finite is important, that they will only discover the phenomena within the size of the meshes of the net, and if you want to get more accurate, you've got to do all sorts of things. And in some instances, computer fluid dynamics, for instance, with turbulent flows, there are important things that are happening at very, very small scales, and it's difficult to follow those. And in computer fluid dynamics, they're fixed by approximations to how that behaves. You don't see those.
No.
It's an off-the-shelf program,
Yeah.
so you don't see the assumptions that are being made. That provides you with a second problem that is you don't see those assumptions which are being made. You don't therefore have a problem with how faithful to reality it really is. It's computer fluid dynamics is like a digital wind tunnel, but with a real wind tunnel you measure things and you get what's really happening. With a digital wind tunnel you get what the computer thinks is really happening.
Yes.
But without some resemblance to the real world, you don't actually know that. Consequently, we always need to go back to the real world and test that the thing is giving us sensible answers.
Yeah.
But the other thing they do is they give us an answer to a particular problem. They don't tell you what is happening inside that, which means that if you want to change things, you've got to have some other method of working out where the right answer is. It will tell you the drag on a wing, but it won't tell you the right wing shape. You've got to put another thing in and keep doing it until you find the right answer.
Which means you still need the understanding of
So you need some other theory, like in fluid dynamics it's boundary layer theory. In stressing there's a whole pile of work that was done that will give you stress formula for particular conditions. There's a big book of it.
Yes, Rourke, famous
Rourke. That has not been put out of the thing, because while the finite element stress analysis will tell you whether a particular structure is likely to break or not, it won't tell you how thin you could make that particular thing without understanding what the mechanism is that determines the stress in that particular element of it.
That's right. It's a lot quicker sometimes to do it from Rourke than to
And
get to
it's both quicker in terms of doing it with Rourke to get the right answer rather than faffing around running the computer. And it also means that when you build system models where you're having to link one phenomena with another phenomena, you've got some basis for putting that in to the model to give you how that bit of the model is going to work relative to something else. You can't be forever going back to a finite element model for every single thing that you change.
Yeah. Anyway, because models do not need to represent all the real system complexities, they can be used right from the start of a project. And it could be argued that almost all of the analytical and decision making in systems engineering is based on models. Even if that is a slight exaggeration, modelling is crucial to the systems engineering process. And in the next video, we'll look more detail at parametric modelling and especially how we use those to estimate cost.